If you look at any past paper for the Cambridge AS and A-Level Physics 9702 syllabus, you're going to see one topic staring back at you every single time: linear momentum and its conservation, specifically elastic versus inelastic collisions. This isn't just some optional side quest you can skim over. This is essentially a final boss fight. Mastering this topic is absolutely essential, and in today's explainer, we are going to decode exactly what the examiners are looking for. We're going to break down both the core physics and the high-stakes exam strategy you need to conquer it.
0. That is the exact number of marks you'll get for an answer that completely ignores the specific context given in the exam question. Seriously, you could write a beautifully structured, scientifically flawless paragraph about momentum, but if you failed to play the role of a data detective, if you don't extract the specific variables provided right there in the prompt, you get 0.
So that brings us to a really crucial question. Why do highly prepared, top-tier students still fail momentum questions? Well, it's time for a quick confession. Let's be totally honest here. Most candidates do not lose marks because they fundamentally misunderstand the basic physics. Not at all. They lose those critical method marks because they completely neglect strict presentation conventions and the deeper vector nature of these concepts. We're talking about proper headings, correct terminology, appropriate formats, and really clear annotation. Top students still make these painful mistakes because ordinary revision usually just focuses on churning out the math instead of focusing on how your scientific reasoning is actually being assessed by the examiner.
Okay, let's build this from the ground up. Precise definitions are the absolute first step to unlocking cross-topic connections. The syllabus heavily emphasizes that top-performing students exhibit connected, conceptual understanding, so you have to clearly define linear momentum as the product of an object's mass and its velocity. And remember, because velocity is a vector, momentum is absolutely a vector too. Direction is literally everything here. But what about its conservation? Well, the golden rule is that the total momentum of a closed system remains constant, provided no external resultant force acts upon it. Listen, that closed system part, it is non-negotiable. If you don't explicitly mention the absence of external forces, your definition is incomplete. Nailing this theoretical architecture right off the bat is exactly what separates average answers from the elite ones.
Now let's talk about a core mathematical difference that examiners absolutely obsess over. In elastic collisions, kinetic energy is perfectly conserved. The objects bounce off each other with absolutely zero loss of energy. Now, realistically, we mostly only see this at the atomic level, like with ideal gas particles. But in inelastic collisions, kinetic energy is not conserved. It's lost to the surroundings. When macroscopic, everyday objects collide, they deform, they make a sound, they generate heat. That internal energy shift means the total kinetic energy drops. And if it's a perfectly inelastic collision, the objects actually stick together or coalesce. Confusing these two scenarios is a fatal error. It is the absolute pivot point for almost every calculation question in this entire topic.
Now you might be wondering what specific clue examiners leave behind that changes an answer completely. Well, in just a moment, I'll show you the exact examiner clue that flips the script entirely. But honestly, to actually spot it during a high-pressure exam, you first need a specific framework. Without this framework, the clue is totally invisible, and you're going to find yourself stuck on questions that should have been super straightforward.
So here is that procedural framework. You need to memorize these 4 steps. Step 1, concept. Step 2, evidence and data. Step 3, scientific reasoning. And Step 4, examiner wording. When you're tackling complex calculation questions, you absolutely must deconstruct the prompt using this exact sequence. First, just state the physics concept, like the conservation of momentum. Then, extract the relevant data from the prompt, making sure to assign the correct positive or negative signs to your velocity vectors. Third, apply your scientific reasoning. This means explicitly writing out the relationship or equation before you plug in a single number, showing exactly how Newton's laws apply to this collision. Finally, present your conclusion using the exact terminology the examiner used in the question itself.
This 4-step sequence is what we like to call the method mark strategy. You see, Cambridge awards points for the process, not just that final number at the bottom of the page. If you follow those 4 steps, you are actively proving to the examiner that you are deconstructing the question properly. You're showing that you extracted the data and selected the right analytical framework. Even if you make a tiny, silly calculator error at the very end, executing with clear notation and this structured process secures you those vital method marks. It's basically your safety net.
Let's actually put this to the test. Imagine a flawed student answer for an inelastic collision. They write, the objects stick together, so momentum is saved, but energy is lost. It's just incredibly vague, right? Now contrast that with a top band answer.
Since the collision is perfectly inelastic, the objects coalesce. By the principle of conservation of linear momentum, total initial momentum equals total final momentum. However, initial kinetic energy is greater than final kinetic energy, as energy is dissipated through deformation and sound. Do you see the difference there? That superior answer reverse engineers the exact framework we just discussed. It uses clear notation and unequivocally correct terminology.
Which brings us right back to that examiner clue I promised you earlier. This is a direct quote straight from the principal examiner reports. Candidates consistently confuse key terminology. Always define terms before using them in extended responses. This is the ultimate authoritative feedback on that previous challenge we just looked at. The hidden examiner clue that changes everything is rooted in how well you define your terms before you even start calculating. If you don't anchor your response with a solid definition of a closed system or an elastic collision, your scientific reasoning just floats away, and unfortunately, so do your marks.
To keep our momentum going, pun definitely intended, let's rapidly break down the top 3 most painful learner mistakes directly from the examiner reports. Number 1, vague details. Examiners want specific evidence and precise vector directions, not broad generalizations. Number 2, bad presentation and formatting. Look, if you're working out as a complete mess, if you omit units mid-calculation, or if you drop a crucial negative sign when an object rebounds, the examiner literally cannot award you method marks. And number 3, ignoring the specific context. Remember that 0 we talked about at the beginning? If the question is about a satellite and a meteor, please don't write a generic answer about 2 cars colliding. Use their context. To help you dodge those traps, here is a highly effective cognitive tool. We call it the visual story method. When you read a momentum question, don't just see a boring block of numbers. You need to visualize the objects before the collision, imagine the actual impact, and picture the aftermath. Sketch a quick annotated diagram right there on the page. Draw explicit arrows for velocity, and label one direction as positive and the opposite as negative. Turning all that abstract data into a dynamic visual story helps encode these complex momentum concepts in your brain, ensuring you literally never miss a directional sign change again.
You have to realize there is a clear progression of higher-order objectives in these exams, and it's broken down into 3 levels. Think of it like climbing a ladder. First is the descriptive level, which is just basic data extraction, pulling the mass and velocity straight from the text. Next up is analytical, where you interpret mathematical relationships, like setting up your initial and final momentum equations. And finally, sitting at the very top is the evaluative level, where you provide justified recommendations and critical analysis. If you want those top-tier scores, you have to move past basic analysis and step up into the evaluative tier.
The exact criteria for that evaluative thinking act as the final hurdle to fully mastering this entire topic. You need to question the assumptions made in the experiment, you need to spot the limitations in the data, you absolutely must evaluate alternative interpretations and explain how they affect the final conclusions. For example, if momentum doesn't appear to be perfectly conserved in a lab experiment, an evaluative thinker isn't just going to say the math is wrong. They will ask, was energy lost to friction on the track? Was the system not truly closed? Top-scoring candidates constantly demonstrate this exact level of critical analysis.
So we've broken down the framework, the math, the common traps, and that crucial evaluative mindset. But that leaves us with a final massive question. How do command words specifically dictate your final mark band in practical data analysis? Because answering describe when the question explicitly said explain is a fundamental misunderstanding of the physics being asked for. It's a brutal trap that catches thousands of students every single year. So how do you decode these command words perfectly so that your hard-earned physics knowledge translates directly into marks?
Well, the answer to decoding those command words ultimately lies in how well you understand the reality of the physics happening right there on the page. Momentum isn't just some arbitrary equation that you balance to get a good grade. It is a fundamental symmetry of our universe. From 2 billiard balls clicking together on a pub table to the unimaginably violent collision of entire galaxies millions of light years away, the rules do not change. The momentum is always conserved. The real question is, when you sit down in that exam hall and look at the data, are you just seeing numbers to crunch, or are you actually seeing the universe at work? Keep that perspective, apply the frameworks we discussed today, and you'll be well on your way to acing this topic.